Okay, hello everyone. My name is Beomjoom Kim. I recently started at KAIST Graduate School of AI as an assistant professor. And today I'm going to talk about meta reasoning for task and motion planning, which is also known as learning to guide task and motion planning. Okay. So the types of the problems that I'm interested in are deploying robots in environments that are complex and unstructured. So for example, you may want to deploy robots to your living room where it can tidy up the place. And you may want to deploy your robot at construction sites where you can help the workers with physically demanding tasks. Or you might want to automate your warehouses using robots, right? And all these problems have some commonalities. And these problems basically entail long planning horizon. So unlike some of the problems that are out there, they require you to plan your actions on the orders of minutes, hours, and sometimes days, if you think about tasks like construction or logistics, right? And these problems also involve hybrid decision space. So if you think about, tidying up your living room, for example, you've got your end goal, which is to, have a clean living room. But you've also got these discrete passable decisions, right? Where you have to decide which object are you going to manipulate and in what order and where are you going to move those objects, right? And there's also this traditional, continuous motion level decisions that actually realizes these passable decisions with the concrete robot motion plan. Right? So task and motion planning is about how you, set up the problem and algorithm so that these intricately related decision process can be, made in an efficient manner, right? So in task and motion planning, more concretely, we're interested in achieving some high-level goal by planning a sequence of low-level motion primitives. So these motion primitives can be things like, pick in place, push, throwing, and etc. And you assume that you're given the model of the world. And these high-level goals could be things like, tidying up your living room, construction, packing, cleaning, and so on. Right? So you got these high-level tasks that you want to achieve, and you want to make decisions both at the task level and at the motion level so that you can achieve these high-level goals. Okay, so what are some of the approaches for solving these task and motion planning problems? So I think there are largely two different approaches. One is learning a policy, right? So you learn a policy, a neural network, basically, that given a state tells you what action you should take in the given state in order to achieve a goal, right? Another approach is to build a planner. So this is more classical robotics approach where you write your planner and you hope that the plan computed by this planner would solve the problem. So what exactly is the algorithm that can learn a policy, right? So I think it's the most representative algorithm. I think there are many different algorithms, but I think the most representative algorithm for learning a policy are these deep reinforcement learning algorithms that had tremendous success in these kinds of game environments. So this is a Atari game suite, right? And it shows superhuman performance in these games, right? And here is the Google's ARM farm, right? Where they collaborated with Berkeley where the goal was to train a policy that can pick up any of the objects that are inside this bin, right? And so they built a farm of robot arms, and their goal was to train a policy using deep reinforcement learning algorithm that can pick up an object in this bin, right? So I think there are advantages and disadvantages of deep reinforcement learning algorithms. I think one of the advantages of these algorithms is that they're fast, right? So if you train a policy, right, then computing what to do next just comes down to making a prediction from a neural network, right? So that's quite fast, right? But these algorithms also have, some of the downsides, right? So these policies that are trained this way tend to be fragile in the sense that if you see a state that is very different from the ones that you've seen in training, then you're likely to make a prediction error. And if that error accumulates, then you are likely to end up at a disastrous state, right? So that's one disadvantage. Another disadvantage is that these algorithms tend to be data hungry, right? So they take millions of data in order to have a reasonable policy, and that's why you have the Google and Berkeley had a farm of arms rather than a single arm collecting the data, right? So these algorithms tend to be data hungry. Okay. So what about the alternative method, the planner, right? So this is more traditional robotics approach where you carefully design the models, you typically from physics, and then you write a planner that can utilize that physics models to accomplish various things. And it used to be the case that robotics decision making was all about writing a planner, but nowadays the learning has gotten so dominant. I feel like I should prepare some of the I should show you some of the things that you could do with a planner, right? So here is a robot planner that utilizes a physics model to move an object from initial location to the target location using a bimanual manipulator. So this is the work that I did with Anthony Simonov at MIT. Right? This is a work by Rachel Holliday. So she modeled the interactions between the robot end effector, the bottle, and its lid, and created a planner that can open the lid of the bottle using a sequence of actions. And this is work done by Fong and Garrett, Kale and Garrett at MIT. And so they modeled the dynamics of this construction robot, right? And they used a planner to build what's called a truss of a building, right? And you can see that it's quite a complex procedure, but nonetheless, the planner is able to solve this problem. Okay, so is this better than learning algorithms, right? So it turns out that these algorithms also have downside and good advantages and disadvantages. I think it's a huge advantage of these planners that they're extremely general. So they typically guarantee a form of completeness. And what that means is that unlike learning algorithm, which cannot perform well if they see a state that is quite different from the ones that they saw in training, these algorithms, given a state and a goal, they'll find you a solution if there is one. Okay? So it guarantees a form of completeness, and it can deal with any of the states as its initial state. But the problem with these planners is that they're quite inefficient, right? So in order to just compute a plan, it usually takes a long time, right? And it does not really have a capability to utilize past planning experience. So what that means is that it's both computationally and data inefficient. Right? So we have these two approaches for task and motion planning problems, right? And the question that I asked myself was, can we have the best of both worlds? Right? And this is where I found the approach of meta planning, where you're using learning to guide a planner, right? So you're still using planner, so you can still guarantee completeness and you deal with many of the states, right? But you get to be faster than pure planning, right? Because you're now using learning to learn from past planning experience how to explore more efficiently, right? So you get to explore the actions that are promising first, and that leads you to a more efficient planning. And of course, I wasn't the first one who thought about this idea of meta planning. So if you look at the paper from 1960 by Marvin Minsky, he talks about how you should use learning to learn a heuristic function to guide the search for the heuristic search. And I think that an example that's worth 1,000 words in this realm of meta planning is this. It's a system AlphaGo, right? That played the game of Go, which is extremely long horizon planning problem at the superhuman level, right? So if you look inside how AlphaGo works, it's actually Monte Carlo tree search, which is a pure planning algorithm augmented with reinforcement learning. So you use planning algorithm, but then you use reinforcement learning to learn policy and a value function from past experience that guides the Monte Carlo tree search. Okay? So, given the success of AlphaGo, one natural question that I asked myself was, can I just directly apply methods in AlphaGo to task and motion planning problems? And, I concluded that we can't just do that. And there are two key reasons for that. So the first reason is in the difference in action space. So if you think about the game of Go, we got this discrete board, right? So you have discrete action space. Now, if you think about a task and motion planning problem, you've got discrete task level decisions, like which object are you going to manipulate in the given situation? And you've also got this continuous motion level decision, right? That, for example, like choosing a base pose for picking up an object. So in task and motion planning problems, we have a hybrid action space. Now, another difference is in the state representation. So in the game of Go, if you look at AlphaGo, it just used the board image as its state representation. But in order to solve task and motion planning problems, we need to encode information about objects and their relations inside its state representation. Also, because of the nature of our problem, we need to be able to encode information that allow us to determine where there's going to be an existence of a feasible motion plan in the given state, because each action in a state will be motion primitive, things like pick and place or push and throwing, right? And so you need to have a sufficient information in your state representation to infer whether or not there's going to be a feasible motion plan in order to decide which action that you're going to take. Okay? So because of these two reasons, we can't just directly apply AlphaGo to task and motion planning problems, right? But nevertheless, we can take the high-level intuition in AlphaGo and apply to task and motion planning problems. So what that means is that we can still learn a value function and a policy, right? And make it to guide a search procedure for task and motion planning. And we've done various different works in terms of planning algorithm, learning a value function and a policy. But today, with the limited time that I have, I'm going to talk about how to learn a value function for task and motion planning problems. Okay, so let's talk about learning a value function, right? So as I said, in task and motion planning, we're interested in making these discrete task level decisions and continuous motion level decisions, right? And what we focus on in learning a value function for task and motion planning problems is that, learning a value function for deciding which discrete action to take, discrete task level action to take. So for example, here, the robot is in this room and it has several different options, right? So you can take an action of picking up object 1, object 2 through object 8, right? And we wanted to know which of these discrete task level actions is the best one by learning a value function, right? So for example, is picking up object 1 in this initial state better than picking up object 2 in this initial state, right? So this is the kind of questions that we wanted to address by learning a value function, right? And what we ended up doing was to learn something called an abstract action value function. So this is an abstract action in the sense that it's abstract in the sense that it does not have a concrete motion plan that actually realizes picking up object 1 or object 2, right? But if you learn an abstract action value function that will allow us to tell that tells us which one is the best, then we will be able to speed up our planning procedure, right? Okay, so how should you actually go about learning this value function for these discrete possible decisions, right? These abstract actions. So there were some hurdles that we have to resolve, and there were largely two of these, right? Two of them, right? So the first one is, how should you design an objective function, the learning algorithm, for effectively learning the abstract action value function from the planning experience, right? And the second question that we had was, how should you design the input to the network? So what should be the state representation that allow us to tell us what the values of a different discrete choices are, right? Okay, so let's see how we can resolve these issues, and let's first start with designing the objective function. So what we're given as a data set is a set of planning solutions, right? So each planning solution consists of a search tree, right? And each search tree is, as I said, is a sequence of discrete task-level decisions and a continuous motion-level decisions, right? And if you follow a certain trajectory, then you lead to a goal, right? For some others, you don't, right? So here we have problem 1 to n, right? So once we have this tree, one thing that we can do to learn the value function or the cost to go is to actually measure the distance from your current state to the goal. So you're in the state, maybe it took you 10 actions to get to this goal. So Q of SA, so this the value of this particular abstract action would be 10. Maybe the value of this action would be 7 or 8, right? And you repeat that procedure for all the states that you've encountered in your, trajectory to a goal. Then you have the target values for your, your abstract action value, right? And then you can basically use the mean squared error loss to learn a mapping from a cost to go, so mapping from a state in action to a cost to go, right? Now, the problem with this approach, I think this is a perfectly sensible and a reasonable approach, but there is an efficiency problem with this approach, right? And that problem is that we only have the targets for the trajectories that led to a goal, right? So we can measure the cost to go for this trajectory that actually led to the goal, but for all the other actions, we don't really have the target values, right? So unless we try other actions and actually get to the goal, we don't really have the target values that we can use the mean squared error loss for, and that causes problems, right? Because we only have a target value for the action that led to the goal. Okay? So to resolve this, we came up with a design principle called pessimism against unseen actions, right? So what we're going to do is that we're going to be pessimistic about actions that did not lead to a goal. We don't know if they will, if you try harder, that these actions will or will not lead to a goal. But we're just going to assume that they won't. Okay, and we're just going to be pessimistic about these actions that are not in the trajectory to a goal. Okay, so what we do is actually learn an abstract action bank function, right, that penalizes actions that were not in the path to the goal. Okay, so let's see what the objective function looks like under this design principle. So here is our objective function, and E here is the set of trajectories that led to the goal, right? And F beta here is the rank value, right? So the first term in this objective function says you want to increase the value of the rank value of the desired action. So the value of the state and action pair that led to the goal. Now, the second term is the max rank value of the actions that were not in the data set. So a set of actions that did not lead to a goal in our data set, right? And we want to decrease its value, right? Because we're taking the max of all these rank values of all these actions, and we're saying maximize its negative value, which minimizes it, right? So what this objective function is doing is basically saying, for the state and action pairs that let's go, you want to increase their values. For all the other actions, decrease their values. Right? And that's being pessimistic against unseen action. So with this, without really having the target values for all the actions, we can still train this rank function that allows us to see which action that we should prefer to explore first in the given state. Okay, so our answer to this question of how should we go about designing the objective function for training the abstract action value function from planning experience is to apply this principle of pessimism against unseen actions, right? But there was this another challenge about designing the input to the network, right? And this input has to have sufficient information about encoding the object relations and to infer the feasibility of different motion plans, right? And so to answer this question, I looked at different planning literature, and there was this overarching theme in guiding a planner, right? So and this theme is to solve a relaxed planning problem, where the relaxed planning problem is a problem that is easier than your original planning problem, right? You solve this relaxed planning problem first, and then use a solution to guide a plan, right? So some examples of this in robot motion planning literature is for this these kinds of trajectory optimization based motion planning algorithms. What they typically do is that they first define a relaxed planning problem by ignoring the obstacles, and then defining a straight line path from the start to the goal state, and then feed that as initialization for your optimization algorithm. Okay. Another example of using this theme is in task planning, where you ignore the delete effects of your action schema in your task planning, right? And then you solve this problem with, that ignores delete effects, and then use a solution to this relaxed planning problem to define a heuristic function, and that's called FF heuristic. And this was one of the groundbreaking results in task planning back in 2001. Okay. So the way people use this idea is that you basically define a relaxed planning problem first from your original problem, and then feed this easier problem as an input to your planner. The planner then uses planning to solve the relaxed problem, right? And then it uses the output of this easier relaxed problem to guide the planning for the original problem. So now what we did basically here was that instead of using a planner to solve these relaxed problems, which could also take a long time, we're just going to use a neural network to solve it, right? So we're going to define a relaxed problem representation as an input to a neural network, and instead of planning, we're going to use learning to solve the relaxed problem, and then we're going to use the output as a planning guide. So if you think about a ranking function that we just talked about, it's solving a relaxed problem. What it does is that it solves a relaxed problem and suggests the rank of these different actions, and that is being used as a planning guide. Okay. So how can you do this for abstract actions, these discrete task-level decisions, right? Picking up object 1 to picking up object A, right? And these are decisions about which object you're going to manipulate, in which order, and using which manipulation permit. Right? So one of the things that we realized was that at least for geometric problems, we can represent the problem abstractly by ignoring the geometric details such as poses and shapes of the objects. Okay, so the full problem entails reasoning about the poses and shapes of the objects, but we're going to ignore this and create a problem representation in an abstract manner, right? So that it defines a relaxed planning problem. So what we did is that we designed something called geometric predicates that encode information such as reachability, right? and also some relational information, right? So is object 1 occluded by object 2, or is object can the object be manipulated into a particular region, right? So these are geometric predicates that we define, and we define our abstract state, our abstract problem representation using this geometric predicates. So here is an example scene of a task and motion planning problem, and our abstract problem representation might look like this, right? So you have reachable object 1 evaluated to false because you can see that there are obstacles that are blocking the path to the object. You have occludes predicate, right? That is evaluated to true for this object 1 because object 2 is blocking object 1, and same thing for object 3 for object 1, and so on, right? So basically, our state becomes a binary vector that that is encoded by, that is represented by evaluation of these geometric predicates. Now, of course, the question now comes down to how do you actually evaluate these geometric predicates given a scene, right? So one thing that we realized was that for these, at least for these kinds of geometric problems, the reachability and occlusion of objects and regions are being represented by these geometric predicates. So these information can be actually computed by a robot motion planning algorithm because these are well-studied problems in this literature. And so basically, we can just use them to evaluate these predicates. So the overall computation goes is that we're given some kind of task and motion planning problems like these, and then we're going to delegate the low-level geometric reasoning to motion planning algorithms, and that's going to give us the abstract state representation, well, more concretely, more abstract problem representation that encodes the information about occlusion and reachability. And then based on this, we're going to perform high-level reasoning to decide which action we should explore first using our rank function. And of course, this state representation is not just a binary vector. It is a binary vector, but it's not. It's encoding some relational information. So we represent it with a graph where each node is representing an information about an object. Each edge is representing a relationship between two different objects, and our F data is represented using a graph neural network. Okay. So here is our planning algorithm plus the guidance provided by the ranking algorithm applied to this problem of packing these blue boxes from this region to this region over here, right? And you can see that the robot is making decisions about which objects that it should clear out of the way, and then where these blue boxes should go so that you can fit all of them into the region, and it's able to finish the task. Okay. Another advantage of defining this abstract state representation is that you can collect the data from this environment that has a very different geometry, right? Here you're manipulating boxes, bigger boxes, but it can still apply to the problem with significantly different geometry. So here the robot's goal is to manipulate the small objects in the shelf, but we're still using the F data, using the data collected from this environment, but applying it to a different environment without retraining. And you can see that it still does a job. Here are some quantitative results. So here on the y-axis is the planning time, and the max time is set to 2000 to solve the planning problems that I showed you earlier. And here is the result of pure learning algorithm that just executes the action that has the highest rank value. And you can see that most of the trials fail, right? But sometimes it succeeds, and when it does, it has a very low planning, very low, computation time because it's just making a prediction from your graph neural network. Right? Here are the results for pure planning, and you can see that it does better. So this is the state-of-the-art planner, right? This is our planner plus our hand design heuristic. And you can see that these algorithms does significantly better than pure learning algorithms in terms of planning time, right? These are the medians of the planning times. And the reason for that is because it's more robust to changes in the states, right? In comparison to a pure learning algorithm. And when you tag on, our rank guidance from the ranking function, it does even faster than the one that is designed by our, the one with the hand designed grids. Yeah. Okay, so the takeaways are that if you have a long horizon task and motion planning problem, you should consider using meta planning instead of pure learning or pure planning alone. That can guarantee speed and completeness. And you should think about using a principle of pessimism against unseen actions to design the data efficient objective function for learning a value function or policy, which I didn't have a time to talk about today, for learning from a past planning experience. And for designing the input to these value function and policy, you should think about using the principle of relaxed problem representation as an input to these networks. Okay? And if you're interested in, we have recently published a paper that put together all the ideas that I had in meta planning at IJR. So if you're interested, you can take a look at that paper. And I'll be happy to answer any questions during the interactive session. Okay? Thank you for your time, and I'll see you at the interactive session.